Hello, welcome to today's special seminar. We will be given by Chris Cox, who is a graduate student at Carnegie Mellon, and he used to be a student here for undergraduate and master's degree. He will be speaking about nearly orthogonal vectors, which is joint work with Boris Bukh and appeared on Archive today.
Yeah.
So wherever you go, and make sure you mention that you studied at the Iowa State.
Do some lip service. All right. Yeah, thanks, Bernard. So today I want to talk about a problem that I've been working on. It just appeared on the archive this morning about nearly orthogonal vectors. So the question I want to ask is, how can you arrange, let's say, d plus k vectors in R to the d so that they're as close to orthogonal as possible. So in particular, let's just define the parameter we're actually going to be working with. Let's call it theta of dk, which is going to be the minimum over all of x, maximum, let's say x not equal to y, in x, absolute value of the inner product of x and y, where x is a subset of R to the d of d plus k unit vectors. And we're just asking, what is theta of d comma k? In this talk, and what we worked on was the case where, let's say, k is fixed, and let's say d is going to infinity. Really, most of our results, we can also allow k to go to infinity as well, provided it's much slower than d, usually little o of d to the half, and our results still work. Okay, so let's see here. Small cases. Theta of d comma 0. So I have exactly d vectors in R to the d. How closely to orthogonal can they be arranged? Well, I could just take a standard basis. All right, that answer is 0. That's pretty easy. Okay, next case. K equals 1. Well, what's one thing I could do? At least in 2 dimensions, you could take the vertices of an equilateral triangle. This will give you inner products of -1/2. In 3 dimensions, you could take the vertices of a tetrahedron, which would give you -1/3. And in general, you could take the vertices of a d-dimensional simplex, and that's going to have all inner products equal to -1/d. So we know that this is at most 1/d, and this is achieved by vertices of a regular simplex. Now we don't know that's necessarily equality right now, but in fact it is. That is the best you can do for k equals 1, is take, well, I guess plus or minus the vertices of a d-dimensional regular simplex. So how could we prove that? Well, let's call this the basic bound. Lower bound. I won't give a proof, but I'll give you the key ingredient. It's fairly simple. Is that theta of dk is always bigger than or equal to the square root of k over d plus k minus 1. And let's just keep in mind we're thinking about k fixed, d going to infinity, so this is roughly square root of k over d. The proof is just an L2 bound. Just look at the sum of the squares of all the inner products and use the inequality, the Cauchy-Schwarz inequality, to have that the trace of A transpose times A is always bigger than or equal to the absolute value of the trace of A squared over the rank of A, which holds for any n by n matrix. So if you use Cauchy-Schwarz in this sense, you can actually prove this lower bound very easily. But this actually answers the case for k equals 1. If we plug in k equals 1, this tells me that actually theta of d comma 1 is bigger than or equal to 1/d. So we know that 1/d is in fact the correct answer here. unfortunately, this is not going to give you the right answer for any other k. And that's what we want to talk about, is what happens for other k. Well, let's first see another way, other than doing kind of an L2 method to prove a lower bound. And let's prove 1 over d in a different way. So, alternative proof.
So when you use min max, it means there is an extremal values exists for the.
Sorry?
When you use min and max
Yes.
instead of infimum and suffimum.
Yeah, so compactness, right? I can just take limits and it's all good because I'm on the unit sphere.
Okay.
Yeah, so I can just apply compactness to all of my sequence of vectors and get an actual minimizer.
Okay.
It's not super important,
So,
but yeah.
so you are saying that such a value always exists.
Yes, yes. It's not just an infimum, just by compactness.
Sorry, just a quick question
Mhm.
now. Is your matrix A where you're applying Cauchy sorts, is it the matrix?
The Gram matrix, yeah.
The
Gram matrix, the matrix of all of the inner products. So A here is going to be where the xy entry is the absolute value of x and y.
okay.
Actually, this is important. This is called a Gram matrix of a set of vectors. We will use that as well to do all of our other proofs.
But it won't necessarily be d by d. Because
No, it's going to be
you're
n
gonna-
by n, where n is the number of vectors. So in this case, d plus 1 by d plus 1. But the rank will be d, because the vectors are coming from R to the d, and that'll be important. So let's do an alternative proof for this case. For k equals 1. Well, again, we're going to say that A is the Gram matrix of x. And let's say, well, we know that we have x. Let's just remember, it's coming from R to the d, they're unit vectors. And size of x is d plus 1. And let's also set epsilon equal to the maximum inner product.
Sorry, again.
Yes.
A is the, or is A transpose A the Gram matrix, or is A?
No, A is the Gram matrix itself. So in this case, because A is symmetric, this is just A squared.
Okay.
Yeah, so this, the trace of A transpose A, in this case over here, is actually going to equal the sum over all x and y of the inner product squared. The reason I'm writing A transpose A is everything I'm doing will also work over the complex numbers with slightly different values. So transpose should be replaced by star to give the appropriate thing.
Sure.
And it shouldn't just be A squared. Okay, so let's set this equal. All right, so let's notice that the rank of A in this case is D, or at least at most D. The vectors come from R to the D, so the rank of the Gram matrix is at most D. Well, A is also a real D plus 1 by D plus 1 matrix. So we know that the dimension of the kernel, well, that's 1. There is a vector in the kernel. So let's pick this vector. Let's pick Z in the kernel of A, but not 0. And without loss, let's say that Z1 is 1, and that's bigger than or equal to the maximum of all other components. Let's just assume that the first component is the biggest, and it's 1. Well, what could I do? I could look at the equation AZ equals 0, and let's just look at the first component of this guy. Write it out. Well, if I actually write it out, this says that the sum, I equals 1 up to D plus 1, the entries of A are xi inner product with xj. So because we're looking at the first guy, we get this times zi, and I know that's 0. Is it easier if I go over there? Let's try it. Let's try the switch. So let's pull out the first term. This tells me that I would have negative z1 times the inner product of x1 with x1. And this is equal to the sum over all I equals 2 to d plus 1, inner product of x1 with xi, zi. All right, all I did was move the first term over. Well, we know that this guy is 1 because x is a bunch of unit vectors. This guy is also 1. So let's take absolute values of both sides. This tells me that 1 is equal to the absolute value I equals 2 up to d plus 1.
Z1 is 1 because you chose it that way?
Yeah, just without loss,
Okay.
right? I could just relabel the vertices, the vectors, sorry. Not the most important, just do it over the largest one. X1 with xi, zi is less than or equal to, well now let's look. All the zi's are at most 1 in absolute value. All of these guys, well these are off-diagonal entries of the Gram matrix, so they're all epsilon at most. And there are d of them. It tells me that epsilon is at most, is at least 1 over d. We're good. So we're able to prove the 1 over d bound without doing any sort of L2. In fact, we're really doing an L1 type argument here. We only ever used a bound on the absolute value here and did some L1-ish. So maybe the same thing could work for d plus k vectors. So d plus k vectors. Well, if we tried exactly the same thing, we would now have A, which is the Gram matrix, which is a d plus k by d plus k matrix, but its rank is still at most d, which tells me that the dimension of its kernel is at least k. So now instead of a dimension 1 kernel, we now have a dimension k kernel to work with. Unfortunately, if I just tried to do the same proof, I gave you just some vector out of the kernel and applied this same idea, I'm still only going to get 1 over d. Well, really 1 over d plus k, right? Which is even worse than 1 over d. So somehow we're going to have to pick the right vector out of the kernel. Now how could we do this? So let's talk about a way just to generate an arbitrary vector out of the kernel. Let's say that n is an r to the, it would be d plus k by k matrix with rank of n is equal to k, and a times n is the 0 matrix. So n is the matrix whose columns form the basis for the null space of A. Okay, so I know any linear combination of the columns is actually going to be that way. So let's write down a linear combination in the correct way. Namely, instead of looking at the columns, let's look at the rows. And this is the trick. I'm going to label the rows as y1 through yd plus k. And I'm going to note that for any v in r to the k, the vector where I look at the inner product of v with y1 down to the inner product of v with d plus k, that this is still in the kernel of A, because all I did was take a linear combination of the columns. So now I have a way of generating an arbitrary vector in the null space just by looking at inner products of k-dimensional vectors. So let's try running exactly the same argument. So by the same argument, I know that I have A times the inner product of v y1, v yd plus k. I know that this is 0. So let's fix your favorite I. Fix some I in bracket d plus k. And look at that row of this equation, and we'll end up getting the sum over all, say, j, inner product xi, xj, inner product of v with yi is 0, and doing the exact same thing we did before, we get that the absolute value of v with yi is going to be equal to the absolute value of the sum over all j not equal to I, xi, xj, v with yj, sorry. Oh, that should have been j. I apologize. Is at most, well, we're going to get an epsilon here, and then we're going to get, say, sum j not equal to I, absolute value of v with yj. Just, again, using triangle equality. Let's put that over to Blackboard. Okay. So let's rewrite this in a slightly different way that says epsilon is bigger than or equal to v with yi divided by, instead of just saying the sum over all j not equal to I could add and subtract in one of these guys and say it's actually the sum over all j, absolute value v with yj, minus a 1, like that little minus 1 there, just the diagonal term. And I'm going to write this in the following maybe silly way. And then I'm going to say sum over all j, v yj minus 1. Not really doing anything. But now, here's the great thing. This was true for all I and all v, so I could put two soups here. So I could say epsilon bigger than or equal to that implies that epsilon is bigger than or equal to, let's say, the soup over all I, and also the soup over all v in R to the k. Because it was true for an arbitrary one.
I'm confused about
Yes.
how the algebra goes. So you have a numerator.
Oh, all I did was, oh,
Yeah.
Okay,
there we
that's
go.
what I said.
Yep. Thanks, Rick. Okay. So now I'm just going to write this down. Let's say that mu is the uniform distribution over the set y1 through yd plus k. Probability mass here. And define essentially the same problem. I'm going to define L of mu to essentially be this quantity based on mu. Let's define it to be the infimum in general over all, let's say, y in the support, and the infimum over all v in R to the k of the expected value, where I take x distributed according to mu, absolute value of x with v, divided by absolute value of y with v. And I can define this for any Borel probability mass. It's perfectly happy. And if I plug it in here, it just kind of gives me a nice way to compress all of this. I know that epsilon is bigger than or equal to 1 over L of mu times d plus k minus 1. It's a nice way to write this problem. Just pull the soups into this guy and they become infimums. All right, we happy? I just rewrote what this said in a better language. All right, and then finally, let's just define, let's call it SL of k. Let's define it to be essentially the largest one of these mu's. So what was special about mu? Well, it had finite support. In fact, we know exactly the size of the support, but let's say finite. And also, these vectors spanned all of R to the k, because they were the rows of this k, rank k matrix down here. So we know that they span all of R to the k. So let's define it to be the supremum of all L of mu, such that mu a probability mass on R to the k, the support is finite, and the span of the support is all of R to the k. So what we've just shown is that because epsilon is bigger than or equal to L of mu, and this was true for any matrix I chose, we could say that theta of dk is bigger than or equal to 1 over SL of k d plus k. So just take the supremum over all of the L's. Worst case situation. Whew. Questions? So what is the point of this? Well, this is a d-dimensional problem here. Theta of dk is looking at all the possible arrangements of d plus k vectors in R to the d. Our first thought was, okay, k is small, d is big, so we've just translated a d-dimensional problem into a k-dimensional problem here. And I like that because k is tiny. So the real question now, and I'm going to try to leave these two definitions out, because they'll be important. So, real question is, what are upper bounds? On this SL of K. I don't like this marker right now. Does this make sense? So one thing to notice is based on this definition right here, it's at most 1. That's good. Right, I could pick y and v just to maximize each of these inner products. We're all good. That's not going to be helpful if we plug it in here. 1, we're just going to get over the 1 over d plus k, which we already knew we could do by just arbitrarily picking a vector in there. So the first thing to notice is, really we're talking about arbitrary probability masses here. That's hard. But we can actually change the probability mass and not change the L function. So how can we change it? It's actually invariant under general linear transformations. So the claim, so I guess I should define something. Definition, if I have mu of probability mass on r to the k, anytime I say probability mass, it's just Borel. Let's just say that. And let's say I have some q, a general linear transformation. You can define q mu by q mu of s is just mu of q inverse times s for every Borel set s. So just the natural rotate your support, or apply the linear transformation to your support. And in fact, anything like this leaves L unchanged. So for every, so let's say for every general linear transformation, L of mu is always going to be the same as L of q. And this is fairly simple to see. Just write down the definition. If I give you any y in the support of q mu, and any v in r to the k, well, the expected value, if I take x distributed according to q mu, x would be y would be, well, I could just kind of pass the q inside, and now just have x distributed according to mu of qx times v, by definition, divided by, let's write this as q inverse y, v, and then just pass the q to the other side. Q transpose v over absolute value inner product of q inverse y and q transpose v. And that gives you a proof. Just pass everything over to the other side, and taking the phelums is all good. So this L function is unchanged by any sort of non-singular linear transformation, so that gives us a lot of power. We can put the probability mass in a nice form. Questions so far? All right. So let's do a little toy bound. Really fun little proof to show that SL of 2 is at most 2/3. So if we show that, that would imply that theta of d comma 2 is always at least basically 3/2 over d. So how can we do this? Well, we're going to be really cute about it. Let's say that C is, so we fix any mu such that the support of mu is finite, you know, and support of mu spans R2. And let's set C equal to the convex hull of the support of mu union negative the support of mu. Now there's a really old result back from the 40s by Vesicovich, which says that if I have any compact convex object in the plane, then I can circumscribe it by an affine regular copy of a hexagon. Okay, lots of words. But what this means is that I have my C out here somewhere. And what I can do is I can apply some Q, a general linear transformation, such that C looks exactly like this. We have a regular hexagon, and C is circumscribed. So this is some C, and this is Q times C. This is the hexagon H. So circumscribing just means that, well, every edge of the hexagon contains a point of C, of Q times C. All right, this is not difficult to prove if you just want to sit down and do it. It's made easier because I actually force some central symmetry of C. And that's just because really I don't want to be able to translate the hexagon. That would change F. So I just want to apply some general linear pattern, assuming central symmetry is good enough for that. Yes?
Quick question. Is mu, let's say, L of mu invariant if
I translate?
if you throw in the negatives, so basically...
No, so no. One, I don't care here, but no. So I can actually always assume mu is centrally symmetric as well, just by averaging x and minus x. It's still going to be a probability mass, and because I take absolute values absolutely everywhere, that's not going to matter. Yeah?
I get you take absolute values absolutely everywhere.
Absolutely everywhere, yes. Okay. We good? So by Besicovich, I can circumscribe this hexagon. Now, how does this hexagon help me? Let's use some purple here. All right, I'm going to draw three vectors. Namely, this is going to be vector 1. This guy is vector 2. This is vector 3. They're the guys that are orthogonal to these sides. Now, because I can just kind of shrink, I can assume that the norm of VI, that they're all 1. Let's just say that. And if I draw these edges, so I'm just going to do some setup, these edges are L1, L2, and L3, where Li is just the collection of all x such that the inner product of x with Vi is 1. So that's just that line. All right. So now here's our question. It's the maximum substitution question. What is the maximum over all x inside the hexagon? I'm going to forget about Q times C here for a second. All x in the hexagon of the sum, I equals 1 up to 3, absolute value inner product x with Vi.
So is the hexagon the boundary, or is it...
Yeah, so this is the hexagon ridge. This is the boundary. I'm forgetting about QC for a moment. Sure. I'm just asking, what's the largest inner product added up with these guys? Well, this is an easy question. H is convex. The sum is convex. So I know that the optimum must actually occur at one of the vertices of H. Great. So if x hat is an optimum solution without loss, x hat is in, let's say, L1 and L2. And then we have a lot of symmetry. Well, so what does this tell us about this x hat? It says that the inner product x hat with V1 equals inner product with V2, which is 1. And the inner product of x hat with V3 is going to be 0. So you can see that this vector right there is actually orthogonal to that vector there. My picture is bad, but you can actually compute it. So we know that this maximum, the answer is 2. Great. Well, so how does this help us? Let's now look at the measure Q times mu, right, which is what we're looking at. I know that Q times C, let's say it like this, the support of Q mu is contained in QC, based on how we've done this, which is then contained in the hexagon H. So I actually can apply this bound and say, if I add I equals 1 up to 3, the expected value over x, all x distributed according to q mu, absolute value of x with vi, this is at most 2. It's passing the sum inside of the expectation. But this tells me that there exists an I such that the expected value x distributed according to q mu, x with vi, is at most 2/3. And then, finally, I'm going to use the circumscribing property. So that I know that every single edge has some vertex of QC. Well, the vertices are just plus or minus the values inside of the support of QC. So I know that there exists some y in the support of Q mu, such that this special I, absolute value of y with vi is 1, lies on that edge, either plus or minus. And this finally tells me that L of Q mu, and let's remember that this is the same as L of mu, is at most x distributed according to Q mu, x with vi, the special I over, the special y with vi is at most 2/3. Just by using our definition of the set of mu function. This is great. Very cute proof. In fact, SL of 2 is 2/3. You can take the hexagon and just see it. So let's remark, this tells me that theta of d comma 2 is always at most 1 over, we said that the SL2 is at most 2/3, d plus 2 minus 1, which I think is 3 over 2d plus 1, or minus 1, one of the two. So we have a bound. Unfortunately, I have no idea how to extend this proof. The most natural thing is, well, it's conjectured that everything in 3 dimensions can be circumscribed by an affine regular copy of a rhombic dodecahedron. The rhombic dodecahedron gives the wrong answer for 3 dimensions. So, however, I could get the right answer in 3 dimensions if you could circumscribe a buckyball, which is just impossible. So we need to do something else to get the answer for all other k dimensions. So let's give the actual value. So the claim is the following. And we'll discuss all of the relevant. SL of k is always at most 1 over the square root of k plus 2 plus 1 minus 1 over the square root of k plus 2 over k plus 1 choose 2. All right, we'll see where that comes from, although I'm not going to give a full proof. So here's the idea. We said that L was invariant under any general linear transformation. So let's try to find a really nice way that we can put every single probability mass. And that thing is called isotropic position. So let's give a definition. I'm going to go back over here. However, I need to leave out the definition of this guy. I'm not very good at organizing my work. Let's highlight this. This one. Okay. So definition. So I have some mu, a probability mass, on R to the k. Mu is isotropic if its second moment is the same as you would get from the standard basis. So what's one fact about the standard basis? I can project any vector on it and just add up the inner product squared and get the norm of the vector itself. So let's, and this is what isotropic is. If the expected value of x distributed according to mu of inner product of x with v squared is 1 over k times the norm of v squared for every single v. Equivalently, if you like it more, the expected value of x distributed according to mu of x times x transpose is 1 over k times the identity. So its average tensor is going to be the identity map scale. So the second guy right here, if you study it for a bit, this guy tells me that if the support of mu spans r to the k, then there exists some general linear map Q with Q mu isotropic. Just simply see whatever this is and just conjugate by the correct matrix. So we can actually assume this really nice form. Now, how does this really nice form help us? Well, let's see here. Let's suppose mu is isotropic. And let's say that L of mu is equal to some alpha. I want to come up with a different way to upper bound L of mu. Well, let's see here. I know, just by using the definition of L of mu, that for every y in the support of mu, and for every v in r to the k, say mu is on r to the k, the expected value x distributed according to mu, absolute value of x with v, is bigger than or equal to alpha times the inner product of y with v. Just by unwrapping this guy, because we're taking the infimum over all y and v. In particular, I could pick a very special y and v. Let's pick v equal to y and average over all y. If I do that, using the isotropic property, I get the following. Here, if I average over all the y's, I get the expected value, let's say x and y, independently distributed according to mu, absolute value of x with y. Well, this is bigger than or equal to the expected value over y, distributed according to mu, of alpha times y with y, just by substituting v equals y and averaging over y. Well, this is alpha, it's the expected value of norm of y squared. And this is going to justify why we actually picked the constant 1 over k here in our average. Is because now, since I have the 1 over k, if I average over all of the norm squared, I'm going to get 1. And to see that, just look at plugging in each of the standard basis factors. I'm going to get 1 over k times the ith component of y squared added up. And that'll give me the norm of y squared, which is 1. Sorry, it's going to give me 1. So what did we see? It's enough to upper bound the expected value of x and y distributed according to mu of all pairwise inner products when mu is an isotropic prop mass on R to the k. This is exactly what we do. I'm going to leave this bound up and write the following claim. I'm not sure how much. About 10 more minutes left. That's good. So what's our claim? The claim is, if mu is isotropic, then the expected value of all possible pairwise inner products is at most 1 over square root of k plus 2. Which, as we just argued, will give the same bound on SL of k. But I can tell you something further. Where does this funny number come from? With equality, if and only if mu is the uniform distribution over a certain structure. Over, and I'll define this in a second, a system of k plus 1 choose 2 equangular lines. Okay, so what are equangular lines? So definition. We give you a subset of r to the k unit vectors. Our equiangular line is said to be a system of equiangular lines if, well, essentially I can think about lines passing through the origin, and equiangular means that all of the angles are the same. So every pair of angles, every pair of lines should meet at the same angle. I don't like thinking about lines and angles, so let's think about vectors and inner products, right? Said to be a system of equiangular lines if there exists some real number beta with absolute value with all inner products equal to beta for every x not equal to y. Of course, an absolute value, because, you know, depending on the direction we pick the vector in. So it's known, and it's not difficult to prove, that if x is equiangular, then size of x is at most k plus 1 choose 2. I guess one thing I should give you is a couple examples of equiangular lines. 2 dimensions, take the 3 lines passing through the opposite vertices of the hexagon. In 3 dimensions, take the 6 lines passing through the vertices of the regular isosceles. These are also equiangular. In fact, this guy right here says that that's the best you can do in dimensions 2 and 3. Okay, unfortunately, this bound is usually not correct. It's only known, so it's known that there exists k plus 1 choose 2 of them for k in, I guess 1 is silly, but let's include it, 2, 3, 7, and 23. I know people who conjecture that it can never ever happen. It can't happen otherwise. One thing that is known is that if there are k plus 1 choose 2 of them, then k plus 2 must be an odd perfect square. And yeah, it's, not much is known about this question. But somehow, this question here is very closely tied to the existence of these k plus 1 choose 2 equiangular lines.
Wait, what must be an odd perfect square?
K plus 2 must be an odd perfect square if there are to be k plus 1 choose 2 equiangular lines. You can get it by looking at, you can modify the gram matrix of these in a particular way. And look at the eigenvalues, and it turns out, using some algebraic complement ideas, you can say that 1 over the square root of k plus 2 must be the algebraic complement of something else, and then analyzing that a bit further, you get that square root of k plus 2 must be an odd integer, just by some, you know, algebra nonsense.
Well, except for, I guess, 3.
Yeah, except for 3, yeah. Yeah, because you need, like, you need something like 2 times k to be bigger than, to get the actual, like, the fact that you can say something about the algebraic complements.
So I assume no one has proven anything about one way or the other about 47, either negatively or positively.
Nothing else is known. It is known that if k plus 2 is not an odd perfect square, then you can get a, I think you can subtract off a linear term from the upper bound on the size. Yeah. So how does this justify this bound? Well, you can calculate that the angle, the beta here, for the k plus 1 choose 2 equiangular lines is exactly 1 over square root of k plus 2. It's not difficult. And then you see, well, if I plugged in a system of k plus 1 choose 2 equiangular lines here, that's exactly what I would get. I would get 1 over square root of k plus 2, except on the diagonal, in which case I get 1. So I should just modify the diagonal. And in fact, this completely answers the question if these systems of equiangular lines exist. So let's write down the big theorem. So first, well, let's just call this the theorem. Always, theta of d comma k, let's define alpha sub k to be this bound here. Theta of d plus k is always bigger than or equal to 1 over alpha k times d plus k minus 1, if you believe everything I've said, with equality, if and only if. I haven't proved the if part, you need a construction, but we can give a construction using these equaingular lines. So if and only if there exists a system of k plus 1 choose 2 equangular lines in R to the k, we'll say and d is negative k mod k plus 1 choose 2. And this is kind of necessary, but anyway. The reason for this is essentially some tensorization trick. And it turns out that it is also necessary. If you don't have this condition, you also get a strict inequality. But the reason it pops up essentially is, well, if I have a construction for like d plus k vectors, and I also have one for like twice d plus k vectors just by doubling down and doing some tensorization. And I have like a couple minutes left. What else do I want to say? Maybe I'll say a tiny bit about how this proof goes. Let's talk about this claim a little bit. So the key idea is abound on the following thing, is give upper and lower bounds on the following thing: the expected value of xy distributed according to mu of the inner product, the square root of their norms, minus square root norm x, norm y, over k plus 2 squared. Now, how do we do that? We actually use the same inequality we used in the L2 norm case, that thing with the trace and the rank. Namely, use the fact that for a general function, if I take some function from some omega squared into R, omega is just any set I want, and I have mu, a prob mass, on omega, then the following inequality holds. I'm not good at space management, let's just write it here. Expected value over x and y, distributed according to mu, of f of xy squared, is bigger than or equal to 1 over the rank of f times the absolute value, expected value, distributed according to mu of f of xx squared, where the rank of f is the natural way to extend matrix rank to infinite matrices. But yeah, so it requires some work doing some Hadamard product stuff, but honestly not that long. And the paper appeared on Archive this morning if you want details, or I'm open to questions as well.
Let's thank Chris for his talk.
Is that equangular lines a standard quantity at research uses?
Equangular lines, yeah. That's a standard thing they're called, unless you're a physicist and you study. So everything we did actually works over the complex numbers as well. Except there are at most k squared equangular lines. And so you have to modify this number to be, and the angle is 1 over square root of k plus 1. So you modify everything with those appropriate values, and it still holds. Weird thing is, over the complex numbers, it's conjectured that k squared is always the right answer. Whereas over the real numbers, it's just not. And in that case, the physicists have, a really weird name for it, called like SICPOVM or something, an acronym for, to make them sound smart. So yeah, it's received a lot of study. And in fact, it's been verified that there are like k squared equangular lines over c to the k for, well, maybe like 100 values if you're a mathematician and a few hundred values if you're a physicist. Depends on if you actually want to know they really are equangular or just equangular up to a certain numerical precision, right? So it is very well studied in both the real and the complex case. It's a strange question. Yeah?
So if I remember from the beginning of your talk, you said theta d2 lower bound asymptotically was square root of 2 over d? Or
No, well, that was the trivial lower bound is at least square root of 2 over d. The right answer is actually 3/2 over d, as we just showed. This shows it right here.
Okay, sorry.
So there are, I didn't prove the upper bound. The lower bound I did prove. That was the SL2, at most 2/3. And this guy, you can actually take the hexagon and do a construction as well. So this answer right here, if I plug in k equals 2, alpha k is 2/3. Plug it in here and we get asymptotically 3 over 2d. Either plus or minus 1, I don't remember. Yeah.
So the improvement of your trivial lower bound is really coming from that second term,
It really is, because the trivial bound is basically square root of k over d.
which is the same.
This
as k
is square root of k plus 2 over d.
Okay.
Yeah, so that's really the difference, is that second term. So here's something funny, is our bound is a strict improvement whenever k is at most order square root of d. Reason for this is the bound on the rank of this function here. Really, we have finite support, so we can just think about matrices. Well, this function is some sort of grand matrix, and we're squaring all of the entries. Well, if you do that, that's just a Hadamard product. And we know how Hadamard squares their rank work. Namely, if I have a rank k matrix, and I take the Hadamard square, its rank is at most k plus 1 choose 2. It's a happy accident that we get k plus 1 choose 2 out of this argument. However, suppose now that I have fewer vectors than k plus 1 choose 2. So d plus k is less than k plus 1 choose 2. That says k is bigger than order root d. Well, I should have used d plus k as an upper bound on the rank of this matrix and not k plus 1 choose 2. If we did that, we recover the trivial bound. So just making that change, we get the trivial bound back. It's really weird. So it really is this extra little winning factor we can get by reducing essentially the dimension of the problem by a factor of square root.
Should I be worried about the upper bound?
We could talk about it.
Okay. I mean,
So I should mention, yeah, sorry, I did not mention. This only gives you an upper bound for those special k's, right? You could ask, what about every other k?
Well, I'm just worried. What is an upper bound for theta d comma k? I mean.
Well, this is also, it's an upper bound when we have a system of k plus 1 choose 2.
Right.
In general, I can give you the following. This is also another one of our theorems. For every epsilon bigger than 0, there exists a k naught, such that whenever k is at least k naught, you know all the general mumbo jumbo, theta of dk is at most 1 plus little 1 depending on d. So the answer is square root of k over d. We can actually get rid of this 1 plus epsilon, for example, if k is like a power of 4, then you can erase that. So the construction isn't easy. Essentially what we do is we try to mimic the idea of these isotropic measures and some tensorization tricks. So we build essentially a nice system of vectors by taking Steiner systems and blowing them up by using Hadamard matrices. In kind of a way that like the first bound of like k to the 3/2 equangular lines was shown, that's slightly different. So we get a nice system of vectors that we can then just tensorize a bunch of times and modify a little bit to get a d-dimensional system instead of from k dimensions. And then in order to actually get the 1 plus epsilon, we have to rely on the existence of arbitrary designs, the Key-Bash result, and also some prime number theorem for arithmetic progressions, and yeah. So it's a bit of work, but the basic idea behind it isn't hard. It's find a nice system of vectors in like R to the k that have this kind of isotropic situation, and then tensorize them a bunch of times and just scale the resulting matrix in the appropriate way. So we can talk more if you'd like.
Okay, thank you.
Let's thank Chris again.
with theta.